Hello and welcome to another Würth Elektronik eiSos webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Compendium about common mode chokes, structure, use, special features and differences explained using practical examples. Our speaker today is our product manager Laurent Völkel. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us your questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The questions from the chat will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, please email us at eisos-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. You can also watch the recording of today's webinar one day later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker, Laurent Völkel, and I wish you an exciting webinar.
Thank you, Eleni, for this wonderful introduction. My name is Laurent Völkel, and I will say welcome to everybody. Today I have the pleasure to talk about some crazy components like common mode chokes. And before we start with the common mode chokes, I will tell you why you should use a common mode choke. Because you want to succeed the EMC test. Normally you have to apply for different tests, like if you want to approve your device for USA, you have to fulfill FCC. If you go to another country like Japan or Australia, or I would say every country who has a kind of large industry, you will have to fight with some approval for EMC. And in European Union, we have this CE marking, which is not something new, but you have to take care about the law because there are some change. I hope you are in mind that you have to apply for every new device the law which is valid from 2014, and you cannot use anymore the old 2004 or even for 2008 released law. The EMC regulation right now is a little bit different, and you have to take care about this 2014 law if you put a new device to the market, or if you make a modification or make an upgrade or whatever. Please, for that, contact your EMC laboratory where you have done the certification and ask them for the updates. Well, it's very important when you start to design the EMC in your device, because when you just focus on your function and you finish your design and you make the housing and everything, and then before you start to sell it, you go to the EMC lab and you find out, oh my God, I have to improve something because I am above the limit. Well, that's actually too late, and it's very expensive, especially when you have to redesign the whole board. In my opinion, the EMC thinking or the EMC design, it's starting very, very early in development phase. Before you have a PCB, when you make and you draw your first schematic, you have to think about if you have like a very simple DC-DC converter and you have today a switching frequency by 1 megahertz is not something spectacular, and you have a 1 megahertz switching frequency, you have to think about how about his harmonics, third, fifth, seventh harmonics. Do I need to make here a very simple LC filter, or it's not my problem, that's the guy from the EMC lab, he must solve that problem? Well, if you do like that, it's difficult. I will suggest use a pad for a capacitor on your PCB where you know that you have a high frequency issue. Put a 0 ohm pad resistor, and if you have a first working prototype, go with your first working prototype to the EMC lab. Maybe you don't need to make the whole EMC test, but make a quick scan to see which frequency are making a little bit trouble and are too high and could be make a trouble for the EMC final qualification. And if you make there a pad for capacitor, you can improve, put a capacitor there. If you have a 0 ohm resistor, you can desolder and put a ferrite bead there, or maybe an inductor. If you was clever enough and you put a common mode choke pad as well, you just open the circuit and put the common mode choke instead of that. And you can imagine you could pass the EMC test, but your first working prototype. Can you imagine this situation? You go with your first working prototype in the EMC lab, and the guy are testing and say, hey, good job. You passed the EMC test, but your first working prototype. You don't need to do any redesign. Can you imagine how it feels that? So I wish to everybody to have this feeling at least once in life. So I can tell you from my experience, the first thing what you will ask, did you really switch on my device? Are your devices also measuring really correctly? You don't believe it on the beginning, but this is the nice stuff. Okay, now depends on different core material which have been used in inductors. You have to take care that not every core have the same reaction in the same frequencies. Different core have different bandwidth and they are reacting completely different. Only just to know the impedance of the ferrite is not enough. You have to know the impedance lossy area, the impedance R, not the impedance reactance, the impedance lossy area, to know where this filter can act really like a filter and not just to shift the noise in a different frequency. So you can see here, iron powder core are acting like a good filter between 200 kilohertz, maximum 1-2 megahertz. If you have at 10 megahertz some noise, iron core won't help. You need a magnesic zinc core. Magnesic zinc core has also limit above, I will say 30-40 megahertz. I will not use them. I will use definitely for 40 megahertz nickel zinc because they are much more effective. Even nickel zinc between 10 to 2 gigahertz can be work from 10 megahertz to 2 gigahertz, but well, there are also some limits. So above 2 gigahertz, it will be difficult to use any more nickel zinc materials. But in this bandwidth, you can now see, okay, where is my noise situated? Which kind of inductor material I should choose for the first, not just a 22 microhenry or the 1 microhenry, it's enough. I have to choose the right component inside, the right used material to filter in the right way. Well, different material have been used, like toroidal for this thyristor triac switcher are always filtered with that kind of toroid iron cores. 90% of common mode chokes are made in magnesic zinc, and 90% of snap-on ferrites or molded ferrites on USB or VGA or HDMI cable, they are made in nickel zinc core. We have some of those also in magnesic zinc, and we have also some manufactured in nickel zinc common mode chokes. So it have to be take care of which frequency you're acting and want to filter something. But in fact, what make that core in for the noise? What happened to the energy? Because we know we have a first law in physics: energy never get lost. It's always transformed in a different form. So actually, these eddy current losses, these magnetizing, demagnetizing losses, make for the ferrite that this energy from the EMC or EMI, it is transferred into thermal heat. But believe me, even if you use a very high sensitive thermal camera and you look to your USB cable ferrite or VGA or HDMI ferrite, you won't see any temperature rise there. But if you ever build a machinery and you put a ferrite core on your cable and the ferrite start running hot, I can tell you, you don't have any more EMC problem. You should have now a safety problem, and I suggest run away fast you can, because this is not anymore EMC problem. You don't talk about 10-20 volts per meter, you have several hundred volts per meter when the ferrite starts running hot. So be aware, ferrite normally should not get hot from the EMC noise. But what happened in fact with this magnetic field? Well, if you take just a simple wire and build something like a spring, like a rod core inductor, and you introduce a ferrite core in the middle, it will happen that this ferrite core channel the magnetic field and you will have a dedicated north pole and south pole. Now, if you drive more and more current to this wire, this magnetic field can bend out to infinite. We talk about by rod core inductor something like a infinite air gap inductor. Now, if you bend this rod core, and you imagine you make with this rod core, which is quite difficult to bend a ferrite, but you can imagine it's a rubber ferrite, then you can build something like a circle. You build now a toroid. In fact, by the toroidal inductor, you make a magnetic short circuit. You put the north pole together to the south pole. In this case, in the toroidal inductor, you catch the whole magnetic field inside. He cannot escape anymore. Now, this is good because he cannot make any more magnetic fields, but it saturates very fast. So actually the manufacturer are playing with these air gaps, because the air gap is something where you can store the energy and you can avoid very fast saturation. Now, what is happening in a common mode choke? A common mode choke is normally wound in, I would say, 99.9% on a toroidal or something like a frame core, which is always a magnetic short-circuited core. Now, we have on one side X number of turns wound in one direction, and the same number of turns we have wound off the other side in opposite direction. This is called a kind of sector wound inductor for common mode choke. Now, what happens if we apply a current through this choke, like a differential mode signal? Okay, if it's this signal flowing from left to right, and you take your right hand and with your thumb you show the direction of the current, and the rest of the finger, if you would catch this wire, it will generate a magnetic field. Now, this magnetic field generated in the core, the current goes through the inductor, go to the load, come back the same current. Now you have to take your right hand and put again in the direction of the current, and you will generate with the rest of finger the different magnetic field. You will have now the compensation of magnetic field. It means the wall induced on the positive wire magnetic field, it will be cancelled on the bottom side with a minus wire. It means almost zero magnetic field in this core. This is by the differential mode noise or differential signal. When we apply now a common mode noise or a common mode signal, what means that? It means on plus and minus wire, the same timing, the absolute identical current. Now, let me make again the right hand rule. Right hand rule, magnetic field goes inside, it's like same like the differential, the current goes through him, but on the minus pole we have again a common mode, the same direction, the same right hand rule. Now, what will happen here? If you apply that, you decide, oh, now we have a turn. Now we have exactly the same direction of the magnetic field in both windings, and now this magnetic field transferred into heat. This is how a common mode works. You have to pay attention that it's not allowed to put on front of common mode choke the minus to ground, and after you pass the common mode choke, again after the common mode choke's right side to put also to ground, because if you put right side to ground and left side to ground, you make a short circuit of this winding, and beginning of that point your common mode choke is very good for your weight of the device. It makes a little bit few grams heavier, but no more function. So common mode chokes must be used only if you can have a separation of the grounds. For outside noisy environment ground and inside clean ground. If you look in the datasheet of the common mode chokes, you will always find two lines. These graphs show once the common mode filtering and the differential filtering. The differential impedance it is because of the leakage of the inductance. Every common mode choke inductance have a leakage inductance. This leakage inductance generates exactly what the signal will see. So if you have a signal maximum 10 megahertz, it won't be affected the signal by the common mode choke, the black line, which is actually for common mode noise, it will be affected by the red line, which is by 10 megahertz just starting, almost nothing. If you have a 100 megahertz signal, it will be affected by 1, 2, 3, 4, 5 ohm. 5 ohm is almost also not so big issue, but it will be affected because of the leakage inductance. Normally you have a signal something like here by 10, 11 megahertz, and then this signal will see this leakage inductance maybe by a few ohms, but the signal himself will generate a very wide band noise in common mode, which will be filtered later if you use a common mode choke by this black line. It means the usage signal will be not affected, but the generated common mode noise will be filtered with couple of thousands or hundreds of ohms. This is by the common mode impedance into the data sheet from common mode chokes. Now, because of the construction, you can have these toroidals in different winding method. You can wind them bifilar. It means take two wire, even it could be twisted pair, put both together in parallel on the same core. Now you take the same wire thickness, the same number of turns, but you wound one wire on the left side and one wire of the right side in opposite direction. Both are common mode chokes, but they have some advantage or disadvantage. The first advantage is by the bifilar inductance common mode choke, that you have a very fast, very short magnetic compensation, because you drive the current through and you drive by the other wire out. You mean you will have a very, very fast compensation of the magnetic field, and you will have a very, very low leakage inductance. By the sector wounded one, you may have for the compensation of the magnetic field a very, very long way from left to right side, from right to left side, to compensate this magnetic field. And because of the core is not 100% homogeneous, because the wire is not always the same position, you will always have a higher leakage inductance, which is not always bad. It's bad for a high-speed signal. I won't use a sector wounded one for high-speed signal. For high-speed signal, you will need a bifilar wound one. But for a power supply where you don't have a data, I will use a sector wounded one, because I like to have some leakage inductance, and I will show you later why. Now, the advantage and disadvantage by the different winding method, it is first of the advantage, it is that you have by the sector wounded one a must, like if you have a high voltage separation. If you have a AC voltage 230 or 400 volt, you need this leakage of you don't want to have a leakage of the of the voltage, and that you will need a separation of the distance by the norm or by the law. If you use a bifilar winding for kind of high voltage, it will be difficult because you are very close to each other, and you have to use a very high isolated Tex A wire, which is expensive. The wire thickness is big, you will not have enough space to wound so much winding, so it's very rare that you have a Tex A wire wounded common mode choke. For data line, where normally you don't have 400 volt on the data line, you can use a bifilar wounded one. You can use also a sector wounded one, but if you data line, it's very slow data. If it's a high-speed data, you will need this bifilar wounded one. Different family are using different winding method only because it is the purpose for data line or is for AC lines, like power supplies. I open here a box of one of the common mode choke, which can be sourced in the same package. One have a part number, the other one have the same part number, just adding a letter S. The Sierra means sector winding. And when I open the box, you can see inside now the toroid is wound in bifilar method or in sector method. Both have the same core, both have the same wire thickness, both have the same number of turns, so they will have automatically identical sectional and bifilar, the same common mode rejection. The big difference is in the graph. You can see the sector and the bifilar wounded one have a very, very big difference in the leakage inductance. Like if you have a 10 megahertz signal and use a bifilar wounded one, you will have zero effect because of the leakage inductance is so small, you will have zero effect of the data lines. If you have a 10 MHz data already by the sector wound one, you may have more like 10-15 ohm already attenuation to your signal because the leakage inductance is quite high. If you have a 100 MHz signal and you use a Bifilar sector or Bifilar wound one, you may have maybe just 10 ohm attenuation of your signal, and if you use the sector wound one, you will have 100, 200, 300, almost 400 or even 500 ohm attenuation of the signal, which is too much, and the signal will be not happy anymore to go through him. So it depends always on the application which kind of winding you have to choose. Now, if you put a snap-on ferrite on the power supply cable, what do you think? Is that a common mode choke? Imagine if you put on a power supply or you have a data line with 2 wires and you put a snap-on ferrite. Can be that already a common mode choke? Well, I would say this is acting exactly like a common mode choke with just one turn. It has a comparison with the Bifilar wound one using only just one turn. Now you have to pay attention. If you are redesigning your device and you want to put a device which is have to replace on the PCB the snap-on ferrite, which maybe was too expensive because that was the last solution. The device was already done, and now you make a redesign. You want to have a solution on PCB. Think about, you cannot use now just 2 chip-bit ferrite because they are cheap. You have to use a common mode choke, and now the trap is open. 99% of common mode choke 99% of snap-on ferrites are made in nickel zinc. 99% of common mode choke are made in magnetic zinc. Now you have already the first difference because of the bandwidth. Even if you have 2 or 3 turns on it, you never reach 1 millihenry, which is normally the starting point of the common mode chokes in magnetic zinc. So you have to choose now, if you had a snap-on ferrite in nickel zinc, also on the board a common mode choke using a nickel zinc core. And the most our cores, when we are coat them red, they are made in magnetic zinc core. When we coat them green, most of them are nickel zinc. When we coat them black, they are nanocrystallines. When we coat them yellow, they are iron cores. When we have yellow and red painting, it's still also iron cores. So you have to pay attention or to ask the product manager or the sales guy which kind of material have been used, if this is right for your application. And if you have just 2-3 turns, the nickel zinc common mode choke, it will be maybe 10, 15, maximum 20 microhenry and never ever millihenry. A power supply, if it generates some common mode noise and you want to filter that, I will always recommend use a sector wound common mode choke and play with and use this leakage inductance, place on front of the common mode choke or X capacitor like 10 nano, put after the common mode choke or 100 nano, and with the leakage inductance you did build for differential noise additional a very nice P filter. You have with one single component filtering for common mode noise, and with the same component and the 2 different capacitor, you filter also in a higher frequency the differential noise, which is also welcome and it's always a good solution. This is an example on a demo board. It was a demo board for a flyback transformer. They had the input filter with a 12 millihenry inductance. Even it was not protecting earth connected, had some Y caps, but you can see it's only just L and N, also 2 wires, not PE connected. Have some Y caps, a X cap, and some discharging resistor. And we make some tests with this filter. We put some bridges, we make a short for the filter, and we make EMC tests with filter and without filter to see the impact. It was very curious when we test the radiated emission for this device, AC-DC power supply, switching frequency 100 kilohertz. Well, from 30 megahertz to 3 gigahertz was almost no impact without filter or with input filter. So this filter was not so effective, not so much. You can see here a little bit by 100 megahertz something, but that's all, not so big impressive. More impressive was when you are looking for the conductor emission. When you're making conductor emission for 150 kilohertz to 30 megahertz and you avoid the filter, so you make a short on the filter, you can see there's a lot of noise there. Well, this is not so good for EMC. It won't pass the EMC test, and as soon you activate the filter, you just open these bridges from the short, you can see, that's the reason why this guy put this X cap and also the common mode choke there, because now it's working quite pretty good and you can fulfill the EMC requirement for conductor emission. This is another demo board. It's using a link switch with a flyback transformer as well. You can see here the common mode choke on input, transformer, some output filter because it's a flyback topology. Here's the snubber located. Then we have additional capacitor called Y cap from primary to secondary. And then we make some EMC test on this device and want to see what happens if we don't use common mode choke and don't use a Y cap, but we make a best snubber possible. The snubber is a need to just kill the leakage inductance of the primary side of the transformer. The best adjusted snubber without common mode choke and without the Y cap, it was impossible to pass the conductor emission test, 150 kHz, 30 megahertz. You can see the noise is quite pretty big. It's impossible. Now, first activate the common mode choke on input. As soon we activate the common mode choke on input, we saw already, this is a massive good impression. It's to make a good work. The noise getting down, but was still not enough because if you look here on the front, still not past the EMC test. So the second point what we made, we took the Y cap, it's a high kilovolt Y cap, from primary to secondary, and we adjust this Y cap in the value where the noise is getting in this area where the common mode choke have the best filter effectivity. As soon as we put this Y cap, we passed the EMC test, and we was happy that with just two components we was able to fulfill even for a noisy flyback topology AC/DC transformer the EMC test. Well, what is this Y cap? Normally every transformer have winding capacity, primary to secondary. If you make these two winding separately, too far away from each other to have no winding to winding capacity coupling, you may have another problem. The leakage inductance will be too big. So actually, transformer manufacturer like also Würth Elektronik, we try to have a best magnetic coupling to keep the leakage inductance small as possible for the flyback topology. But with this, we will have always a winding to winding capacity. So the noise will pass through this winding to winding capacity. If you now are clever and you put by yourself a Y cap from primary hot to plus side, close to the transformer, to secondary ground, you can play with this capacity, and now the noise will take that path which you can by yourself tune it. The winding to winding capacity is just by accident, and this cannot be controlled very well. It is a value which can jitter. This capacity, you can go and select the capacity in a range from 470 pico to 4.7 nano, the maximum value, and high kilovolt, of course. And with this value, you can adjust that the noise is going in that area where your common mode choke have the best rejection, the best filtering, and you make your life happier and you pass the EMC test. Well, the advantage of the common mode choke, they are very big if you have a special digital signal. If you have a digital signal, like here there is rectangle signal, and you may want to filter the noise on that, and you put on these two inductors, inline inductors have a not so good behavior, because when you are switching on this inductor by the rise time, the inductor will say, friend, slowly, don't stress me. I am loading very slow. As soon you make from high to low, these inductance have again something against you and say, hey my friend, I have some energy. What I should do with this? I will give you now slowly back. And this rectangle signal slowly will be not so rectangle anymore. It's slowed down by the rise time, it's slowed down by the off time, and some driver will not be funny to understand what you want to tell him. They will not understand like a digital signal. They will say, I don't know, this is error. So what to do now? not using instead two separate inductor, how about to couple this inductor on the same core? If you use that in a common mode choke, it means this noise which is coming with him, it comes by common mode, and the signal himself is going in and going out in the same time. It means he will cancel himself. The signal himself, it will be cancelled, but the noise which is coming in common mode on both lines, he will be break down and filter it. This is almost an intelligent, artificial intelligent common mode choke. Actually, I should tell to my people from marketing, they should sell it like artificial intelligence, because they can distinguish between noise and between signal. It's very clever, right? Well, okay, signal is not affected, but the common mode, it will be filtered. This is a very nice experiment. If you have like a signal by 10 megahertz, and on the EMC you can see already at 11 megahertz a noise. If you're lucky and the 11 megahertz is not a differential noise as well, then you can use a common mode choke. If it's a common mode noise, the 10 megahertz signal, he can go through him. Even by 10 megahertz, he's not the best ferrite core for 10 megahertz, but he's lossy. By the compensation, it won't be that much losses, but by the noise, it will eliminate the noise at 11 megahertz, and you don't need an artificial intelligent filter, just an artificial intelligent common mode choke. We should patent that. Okay, we made some nice experience with a USB 1.0. It's a few years ago. We put some webcam to a motherboard, and we make some measurement points, and we start to measure this eye diagram. And with the core and with the generator, we introduce some noise to make this USB cable in common mode very noisy. On the motherboard, directly on the driver before the connector, very close to the IC, we made this wonder eye diagram, which is look perfect, ideal, working, everything is fine. As soon you switch on this generator and you measure in front of this USB connector before the common mode choke, you can see already the eye diagram is quite very dirty, and the trigger already don't work quite pretty good because it's too much noise. If you put now a common mode choke and you measure after the common mode choke, you will not have the ideal constellation absolute without any noise, but you can see the trigger is working, the dots are not so, it's close but not so affected, and we start to measure the data error of this eye diagram to see what is the impact of different value of the common mode choke. First of all, we did introduce a common mode choke with only just 32 ohm. Then we increased to 41, then to 77, and we always count the promille failure rate. And the failure rate by 32 ohm was 3.4, by using a 41 ohm common mode choke 2.55, so it's decreased. By 77 ohm decreased to 2.05 promille, and finally by 363 ohm, it's a USB 1.0, I have to mention, the failure rate was 0 point something. So that's a good impression of common mode choke. That's very good. We can really say common mode chokes is this worth to introduce from some devices. Many people think, oh, the common mode choke is nice to have, it's too expensive. I want to put 2 chip-bit ferrites. They're much cheaper. Okay, we make the same experience in the same footprint. We just take the common mode choke out and we put ferrite bits. Already by a ferrite bit of 35 ohm, we saw that the eye diagram is not anymore looking so nice. Increasing to 110 ohm, the eye diagram, it was not eye diagram anymore. The fail rate increased to 4.4 by 110 ohm, 7.5. We decide make no sense to make further experience because it's just wasting time. 2 chip-bit ferrites will never ever replace a common mode choke. You can use in a USB a chip-bit ferrite, but filtering the 5-volt DC voltage. This is another problem. But don't put on the data line. This is not a good idea. Layout recommendation. You can do also with layout sometimes crazy things. I can tell you from my experience, a customer had to pass an EMC test. We was together in an EMC lab, and we soldered by air using a air PCB, just wires, and we soldered a common mode choke and 2 capacitor, and he passed the EMC test. Finally, his homework was go home, put that on the board, and certified. I tell him don't change too much on the board. Try to avoid any change on a different place because maybe it will generate some different, and you scratch on one side and itch on the other side. So he made the redesign number 1. Noisy area is going in, noisy area is going out, and actually it should be filtered, but it's again noisy. He say he did not pass the MC test. I say, come on, we was together. Did you use Würth Electronic components? He say, yeah. Okay. Did you use the right? Yes, he used the right one. I saw the schematic. It's correct. Then I asked him for the PCB. When I saw the PCB, I said, maybe this is a problem because you had a little bit less noise, but not enough. And how about to go in the common mode choke one side in and one side out? Avoid to interfere that so close to the noisy area. Redesign number 2. One side in, one side out. Already this made so much that it was better like that, definitely. But this was already not the same effect like we had in the air PCB. And finally, when he made the redesign number 3 and used like a galvanic, like it's a transformer with a galvanic connection, then he keep this far away distance, noisy area to the clean area, and he was happy that he got the same results like we did have together in the soldering by air. If I would not see with my own eyes this measurement, I was saying, what the hell? How can so small PCB change make that EMC test it's fail or pass? So from here to here, it's not a big issue, but it's sometimes very, very interesting that you can fail only because of the tracks of the PCB. If you want to know more about this common mode choke, how they acting, which kind is good for your noise, which is not so good, I can recommend go to this RedExpert website. We have an online tool on the website, and you can select the common mode chokes independently of the current, of the voltage, of the size, and you can see directly which impedance and insertion loss they have, and you can select the right component. If you register even, you can put multiple different marker and cursor. If you have the response from the EMC lab, you can just have to put all these peaks frequency here with the marker, and you calculate the minimum in attenuation, and you can choose the right component. If you're using some different ICs like TI chips, you can go by the WEBENCH. Is also here a link. You just start this. If you go to the PDF, and you will get this PDF, you just have to open this WEBENCH, and you can tune your DC-DC converter with this button. It's very easy to decide high efficiency or low cost or smallest footprint, and automatically it lists you which components can fit and not fit to your requirement. LTspice, we have the model in LTspice. If you are not having the latest version, you can go to our website and download the library of the Würth Elektronik, sometime LT, now analog device. They are updating only just once per year the library of the passive components. They update their own active components, but the passive only just by once. And if you want to have the latest library, just go to our website toolbox and open the LTspice folder and just unzip it in your folder from the LTspice, and you can have all these models of the common mode chokes in your simulation, and you can really nice simulate already with LTspice conducted emission. If you have the model of your transformer, well, we have model for our transformer, and if you use our transformer with the chip and with the common mode choke, and you have a model for the listen, it is quite complicated to get it, but it's possible. If you just measure it with a network analyzer and have the S parameter of that, you can introduce in the box and you load the S parameter there. You can predict already with LTspice conducted emission. I'm really amazed about Mike Engelhardt, how funny it is. Free of charge software can do so interesting things like even simulating conducted emission. So it's really crazy when you measure and you see it's almost the same. It is exactly like expected. And if you have a good model of the components, of course it will give you the real values. You want to know more? We have some nice books like Trilogy of Magnetics, already the 5th edition. Please just ask our sales representative or go to the DigiKey website or Farnell website and you can order that. Also on our website you can get a copy of that. Just please ask your sales guy or representative to get one of these books. They're quite very good described and not described from professor from the university. It's from engineer to engineer language and really describe you the effectivity of different filter and why you should use this one and not the other one and where are the tricks. Now, if you have any question, I think we are good in time. Yep. So I will open now the questionnaire and let me see which question did you place to us.
So Laurent, thank you very much for this great webinar. In the meantime, while we are checking your questions, I would just draw your attention again to the fact that you will be receiving the recording of today's webinar or the link to the recording of today's webinar in a separate email. This will be in a few days, and you will also receive in this email the presentation of today's webinar, so you can watch and read everything again. So the first question is, when does a CMC saturate?
Well, this is a really good question. A common mode choke saturate as well. Yes, it is something which is you will not find in a data sheet because it's very difficult to well, it actually can be calculated and also measured, but it is not part of the data sheet because when you drive the standard useful current or signal, you have a current compensation. Only if you don't have a really back path. So if you can guarantee that your current which is going through the common mode choke, it's the same current will take the common mode choke when it's going like minus back, you will have a 100% I would say deleting of the magnetic field and you will have no saturation. If you have a leakage around of the common mode choke and you don't have the same current which is coming back, then it will saturate quite very fast. Another thing, if you have a very high common mode noise, extremely high common mode noise, a small toroidal ring will saturate also very fast. It has to be changed to a bigger core, so it's not so easy to define when the common mode choke is saturated. Like for a power inductor, it's quite very easy. You have the saturation line, but this really depends on how many turns he has, how big is the leakage inductance, and with this you can even make a good calculation, but it's not so easy to make a really definition when it's saturated. Definitely, if you have a such big EMC noise that your common mode choke is saturated, I will say, this is not possible to kill this huge noise only using a common mode choke. Maybe you have to think about some Y caps, maybe you have to think about some other issues as well. Yeah, this is not so easy. It's not so easy, definitely. Another question.
The next question will be, why are the ring cores for a CMC painted in different colors?
Yeah, we use different color for define the different materials. Like I told you before, we will have some core which is painted in Bordeaux red, which means it has manganese zinc core. The material, if it's nickel zinc, it's almost painted in green color. When it's a nanocrystalline core, another different material, then we use whatever a plastic case or paint them black. So the color of the core, it's telling us about the material which have been used. The problem is if it's a capsulated device, you cannot see the color. If it's an open inductor, you can see, and then you can see the according to the color which kind of material we use for these common mode chokes.
Okay, thank you for this. So another question is, Laurent, is it possible to use a CMC as a transformer?
Oh yeah, yes, this is possible. Even it's not made for that, but it can be used like a one-to-one transformer. You have to think about only just you cannot use it like a flyback transformer, but in some cases I saw many customer who was looking for a very low cost and simple transformer, and if it fits for the inductance value, you can use like one-to-one transformer. Of course, we don't give only any data about BH curve or something like that, but in many cases, if the material fit, if the inductance fit, it can be used like a one-to-one transformer, even it's not defined and is not specified.
Are CMCs only available with 2 windings?
Normally the common mode chokes are with minimum 2 windings, but we have them also in a function like 3 windings on the same core, even with 4 windings on the same core. And if you need more like 6 winding, you can go to the transformer area, you can choose this WE flex transformer without the air gap, and then you will have 6 identical winding on the same core, which also available like a common mode choke. Choose please without air gap, so not choosing the flyback transformer. Use transformer without air gap with the same number of turns, like the flex transformer, or using 6 current. So 2, 3, 4 or 6 is possible. It's one wire common mode choke, sorry, is still not in our intention to patent it, and we don't have that.
So we have one last question which we would like to answer. It's how to choose the right inductance value of CMC which suits for my application.
Okay, so normally you're not looking just for the inductance value. You should choose because of the impedance or because of the insertion loss. Always ask the manufacturer for this data sheet. Like Würth Elektronik, we provide you the impedance curve or the insertion loss curve, and actually you choose the common mode choke not because of his inductance. You choose the common mode chokes because of his insertion loss or because of his filtering effect in the area where you have the noise. So the inductance value, it is also possible can be used for calculation of the frequency, cutoff frequency, whatever, but the most important is not to focus on an inductance value. Focus better on the insertion loss curve or impedance curve where you want to filter something.
We're done with our questions for today. If there are any questions which are not answered now, we will try to answer them via email. If not, you can email us as well. Thank you very much for your attention. We hope that you liked our webinar. Thank you, Laurent.
You're welcome. And I have a last message. Please, never give up. There is always a solution. Don't give up if you have an EMC issue. Maybe it's not the common mode choke still manufactured which you can use, but sometimes it's very simple to solve EMC issues. We try to help you. Just call us or contact our sales field engineers or field application engineers, and please keep in touch with us. We can supply you worldwide the same service with the same part number. Everything what is red covered is covered by our own salespeople. We have just few countries where we are using distribution. And if you go to our website, you can also get some additional information. In the toolbox, there are many interesting things which you can choose it. And if you want to keep in touch, I have also a Twitter channel. You can use also the YouTube channel from us, or even our landing page if you want to get some more information. I really thank you for your participation and your attention. Maybe we will meet us in some seminars or an exhibition next time. So, bye-bye.